We're now going to do a brief review of inverse functions. Now we're going to study inverse functions here because we want to eventually look at the inverse of the natural logarithm function. So we're going to look at the inverse of the ln of x. And as it turns out, the inverse for this function is the exponential function e to the x, which is a function that you may have seen before. Now this is a very important function in mathematics and physics and many other fields of science. And in order to understand this function, we need to understand it as being the inverse of the natural logarithm function. So we're going to do a quick little review here of inverse functions. So first of all, recall this. If we're given a function f of x, in which f of a equals b for any two numbers a and b, then the inverse of this function, call it the function g of x, has the property that g of b equals a. So that's what an inverse function does. If your function f takes a to b, so f of a equals b, then the inverse is going to take b to a, so g of b will equal a. That's how an inverse works. Now this gives us the formal definition that we have down here. So a function g of x is said to be the inverse of some other function f of x if the following two conditions hold. First of all, f composed with g of some value x, which is f of g of x, must always give you back x. And similarly, g composed with f of x, which is g of f of x, must also give you back x. These two properties are easy to see if you consider what we just discussed up here. For example, if f of a equals b, then the inverse function, call it g of b, must give you back a. So the inverse goes in the other direction, so to speak. So if we look at f of g of b, well then this is equal to f of a, because g of b is equal to a, and this is equal to b from this right here. So you see f of g of b must give you back b. Similarly, if we look at g of f of a, now f of a is b, so that's g of b, and g of b is a, and so you see we get g of f of a equals a. And so you see that's where these two definitions are coming from, thinking of this property up here as having to hold. Now some notation here. The inverse function g of x for a function f is usually denoted like this, f to the negative 1 power of x. Now keep in mind this does not mean 1 over f of x. Alright, so in this case we're not thinking of f inverse. It does not mean 1 over f. Okay, 1 over f is not going to be the inverse of a function f of x normally. Okay, so this is the special notation we use here to denote the inverse for a function. Now something else to note down here, as we discussed up here, if f of a equals b, well then that means that a comma b is on the graph of your function y equals f of x. And then the inverse function has this property, g of b must equal a. So that means that b comma a is on the graph of your inverse function y equals g of x, or y equals f to the negative 1 of x. So keep that in mind. If this point is on the graph of f, then if we flip these values, we get a point on the graph of the inverse function. Now let's take a look at an example down here. So if we're given f of x equals 3x plus 5, let's find the inverse function and sketch the graph of each of them. Alright, so to find the inverse of this function f, this is normally how we do it. We let y equal 3x plus 5. Now what we want to do here is we want to solve for x in terms of y, and that will give us our inverse function. So if we solve for this x in terms of y, this will imply that, and then solving for x, we get that. And now what we do is we change the letter x to a y and the y to an x, and we'll get our inverse function. And this is f inverse of x. Now let's take note of something here. Let's just pick a few points here. For example, notice that f of 1, let's say, so suppose we put 1 in here for x, we get back 8, right? So that means that 1 comma 8 is on the graph of f of x. And if I look at f inverse of 8, so if I put 8 in here for x, I get, and this is going to be 3 over 3 or 1. So you notice that we get back exactly what we should. F of 1 is 8, and f inverse of 8 gives us back 1. So 8 comma 1 will be on the graph of f inverse. And right over here we have the graph of both of these functions here. Now the blue curve here, that is the graph of the original function. And the red curve down here, that is the graph of our inverse function. And we can write our inverse function as x over 3 minus 5/3. So this is the inverse, this is f inverse here, and this one is f. Now you notice something interesting here. You can recover the graph of f inverse from the graph of f by taking the graph of f and just flipping it around the line y equals x. Alright, that's the diagonal line y equals x. So if you take the graph of f, flip it around this line, you will get the graph of f inverse, and that is always going to be true. That's how you can recover the graph of f inverse. In particular, the reason that is because, for example, over here, look at this. 1 comma 8 is on the graph of f, so that point is like right about here. Right there is 1 comma 8. And if we move over here and graph the point 8 comma 1, you'll notice that that is right here. And so you see, if we're given the point 1, 8, to get to the point 8, 1, we just have to move across the diagonal line y equals x an equal distance. And we move across it in a perpendicular manner here, and we get the point 8 comma 1. So that's why if you take the graph of your original function and flip it about the main diagonal, you'll get the graph of your inverse. And so that's because if AB is on the graph of f, then BA will be on the graph of f inverse, and going from here to here is equivalent to moving across the diagonal line y equals x in a perpendicular manner. Now let's take a look at this. Now before we move on to our next example, Let's just take note of something here for this problem that we just did. Our original function was 3x plus 5, and we found that our inverse was x minus 5 divided by 3. Let's just verify that f of f inverse of x. This should give us back x. Let's just verify that. So if we evaluate this, this is equal to 3 times the inverse function. And now for f inverse, I substitute x minus 5 over 3. Cancel the 3's, cancel the 5's, and we get back x. And that's what we were supposed to get. Also, let's just verify that this should also give us back x. And if we evaluate this, we get, substituting in f for the x right here, and then we get, canceling the 5's, we get, and you see we also get back x. And so that verifies the precise definitions for the inverse function. Now let's take a look at this example. Now before we look at our next example, let's take note of some general results. The first result here is what we've already noted, that if you're given the graph of a function f of x, then the graph of the inverse function can be obtained from the graph of the original function by reflecting it about the line y equals x. Now this implies that the domain of your inverse function is going to be the range of the original function f, and the range of the inverse function is going to be the domain of the original function. So in other words, the range and domain flip. Now that'll be illustrated nicely with this next example. Now one other thing to note before we do this next example, let's recall how to complete the square, because we're going to have to do that in this example. So if we're given a quadratic like y equals x squared plus bx plus c, to complete the square, what we do is this. We take the value b here, we divide it by 2, and we square it. So that'll give us a number back. So we then add it in to the right-hand side and subtract it back out. So we haven't changed anything. You see these two terms here just cancel, and we get back x squared plus bx plus c. Now, before we cancel them, however, take note that this part right here can actually be factored. It's actually equal to x plus b over 2, the whole quantity squared. And then this piece right here is just a number. It's actually this part right here. So that is called completing the square. So notice we take something like x squared plus bx plus c, and by completing the square, we're actually writing it as x plus, let's say, call it some number k squared plus h, where the k is the b over 2 and h is c minus b over 2 squared. So this is called completing the square. Now, let's look at this next example now. We're going to find an inverse function here. Now let's take a look at this example. So we're given the function f of x equals x squared minus 2x plus 3, but we make a restriction on the domain. It's only going to be all the x values bigger than or equal to 1. And we want to find the inverse function, sketch the graph of each, and note the domain and range of each. So to find the inverse function for this, recall what we do is we set y equal to, and we want to solve this equation for x in terms of y. So to do that, we're going to have to complete the square, like we noted here. So now in this case, the b is -2. That's the b right here. And so we take negative 2 divided by 2, that's going to be negative 1, and we square it. So negative 1 squared is 1. So what we're going to do is we're going to put in here like that. So this 1 right here is the b over 2 squared. And then we subtract it back out, so we haven't changed anything. Now notice we can write this now as this term right here will become x minus 1 squared plus 2, negative 1 plus 3 being the 2. And so now what we have to do is we have to solve this equation for x. So take the 2 over to the other side, and we'll take the square root, and what we get is this. So there, I took the 2 over to the other side with the y, and then took the square root. So we get x minus 1 equals plus minus the square root of y minus 2. Now, the reason we need this plus minus, notice, is just recall that if I gave you an equation like x squared equals 4, you would say that x is plus or minus the square root of 4, which is plus or minus 2, of course. You see, positive 2 is a solution to this, and negative 2 is a solution to this. So when you take the square root like that, you have to introduce a plus or minus. Now continuing to solve this for x, we get then that now at this point we have to decide, do we want the plus or the minus here? Well, if you look back at the domain for our function, x is supposed to always be bigger than or equal to 1. So that means we have to choose the positive part. If I put a negative in here, if I took 1 minus a number, that would make x smaller than 1. So we have to have the plus part. So now this dictates that we use the positive part, and we get that. Now reversing the roles of the x's and y's, we then get our inverse function. And this is f inverse. Now let's take a look at the graph of each of these functions and then note the domain and range. So right here, this blue curve is the graph of our original function, x squared minus 2x plus 3. That's the graph of f. And the red curve down here, this is the graph of our inverse function. Notice how we just reflected about the line y equals x to get the graph of the inverse function. Now also notice that the graph of the original function f, we can see that the domain goes from 1 to infinity. And that was actually defined for us. Remember, the graph of the function f was defined with x bigger than or equal to 1. So notice that the domain of f, that's 1 to infinity. And we can see from the graphic here that the range is going to go from 2 to infinity. Remember, the domain always appears on the x-axis and your range is always on the y-axis. So all of these numbers here are in the range for this function, because if we go over, we do hit the graph somewhere. So this number is in the range, this one is, but we can see that the number like 1.8 is not in the range of f, because if we go over, we don't hit the graph. So therefore our range of f is 2 to infinity. Now if we look at our inverse function, right down here is our inverse function, and we look at its graph, well, let's notice one thing here. The inverse function is only defined for x bigger than or equal to 2, right? Because I need that For my inverse function, we need x minus 2 to be bigger than or equal to 0, or else we would be taking the square root of a negative number, and that means x must be bigger than or equal to 2. So that's actually the domain of the inverse function. You can also see that from the graph. Notice how the function only is defined for x going from 2 to infinity. After we flip this about the line y equals x, we get the graph of the inverse, and we see that that only goes from 2 to infinity. So we see that from the graph as well. Also notice the range of the inverse function. Well, we can see from the graph that if we go over it this way, it only goes from 1 to infinity. We can also see that from the definition of f inverse here. As x goes from 2 to infinity, this quantity right here is going to go from 1 to infinity. You see, if I put 2 in here for x, the square root of 0 is 0, so we get 1 plus 0, that's 1. And then as x increases from 2 to infinity, this number here is going to increase, so this quantity is going to go from 1 to infinity. And so you see here's our range for f inverse. Notice also how the domain and the range of f and f inverse flip. So the domain of f is the range of f inverse, and the range of f is the domain of f inverse. Notice how they flipped like that. And so that illustrates the previous result that we saw. And so that completes this example. So now we want to take a look at when a function has an inverse function. And as we'll see, that's dependent on whether or not the function is one-to-one. So to start, let's consider this function. Suppose we look at f of x equals x squared. Now, as we'll see, this does not have an inverse function. So let's see why. Well, if we look at f of 2, if I put 2 in here for x, notice we get back 4, and f of negative 2 is also 4. So therefore, we have trouble defining what f inverse of 4 is. F inverse of 4 would then be both 2 and negative 2. However, a function is only supposed to give you back one number, not 2. So therefore, f inverse, the inverse of this function, is not itself a function. And to understand that graphically, let's take a look at this. So right here is the graph of y equals x squared. And if we draw a horizontal line, right there's the line where y is equal to 4. And notice that f of negative 2 and f of positive 2 both give us back 4. So we see this function is not one-to-one because it fails the horizontal line test. This horizontal line crosses the graph at 2 or more locations. Now, if we take this curve and we flip it about the diagonal line y equals x, this is what we get. So there's the diagonal line. We want to flip this graph around this line, and that'll give us the graph of the inverse. But when we do that, you see what happens is this. We get this curve. So that's the graph of the inverse for y equals x squared. And you see this horizontal line gets flipped to a vertical line. So it gets flipped to this line right there. And so you see what happens, since the original function did not pass the horizontal line test, meaning it's not one-to-one, the inverse graph will not pass the vertical line test. A vertical line crosses the graph of the inverse at 2 locations. And so this tells us when a function will have an inverse function. So a function will have an inverse function as long as it is one-to-one, which is the same as saying it passes the horizontal line test. And that's what this next theorem tells us. Now this theorem makes the following statement. A function f has an inverse function if and only if f of x is 1 to 1, meaning it passes the horizontal line test. Now the if and only if part means you can go in both directions. You can say that if you have a function f that has an inverse function, then f of x was 1 to 1, and correspondingly, if f of x is 1 to 1, then it does have an inverse function. And you can see that this is true from our previous discussion about 1-to-1 functions, and just recall this over here from our previous discussion as well. Whenever you take a horizontal line and flip it about the main diagonal, y equals x, it becomes a vertical line. So if you have a function that is 1 to 1, it passes the horizontal line test, then the inverse function will certainly pass the vertical line test, because this horizontal line becomes a vertical line. So if this horizontal line is crossing the graph of f at only one location, then the vertical line will cross the inverse graph at only one location as well. Now let's recall this result from Calculus 1. If you have a function f and you know that its derivative is positive for all x in its domain, then that function is strictly increasing. Now sometimes you'll see this word monotonic in there. Don't worry about it. It still just means strictly increasing. And this is just your definition for strict increase down here. F of a is less than f of b whenever a is less than b. And you can certainly see that this is true. Recall, if I have the graph of a function whose derivative is positive, so right there's the graph of a function with a positive derivative. Notice every tangent line has a positive slope. Then that function is certainly increasing. Similarly, if your derivative is negative for all x in the domain, then your function is strictly decreasing, meaning f of a is larger than f of b whenever a is less than b. So that's a result just from Calculus 1. Now we have this theorem that relates strictly increasing and decreasing functions to one-to-one functions. So this theorem makes the following statement. If f of x is strictly increasing or strictly decreasing on its domain, then it is going to be 1 to 1, and hence it does have an inverse function. And you can easily see that if I draw the graph here of a strictly increasing function. So there's a strictly increasing function. Of course, it must pass the horizontal line test. The only way it couldn't pass the horizontal line test, you see, is if it did something like this. But then it wouldn't be strictly increasing anymore. It would be increasing here and then decreasing over here, so it wouldn't be strictly increasing everywhere. So if your function is strictly increasing or decreasing, then it does have an inverse function because it is 1 to 1. So let's take a look at this example. Let's show that this function, x cubed plus x plus 1, is 1 to 1, and hence it does have an inverse function. So all we have to do is show that this function is strictly increasing or strictly decreasing. So to do that, we can just take its derivative and show it's either positive or negative. Well, if we take the derivative of this function, we get 3x squared plus 1, which of course is positive for all x. It's positive for all x because, of course, x squared is positive. 3 times x squared is going to be positive, and then you're adding 1 to it. So, of course, this quantity is positive for all x, and therefore f of x is strictly increasing. And that of course implies f is 1 to 1, which means it does have an inverse function. And there we go. Now, notice we didn't actually find the inverse function here. That would be a little tricky for this one because it's a cubic polynomial, but we at least know that it does have an inverse function. And actually, here's what the graph of this function looks like. And so here we have the graph of our function f of x. It's the blue curve right here. So that's the graph of our function x cubed plus x plus 1. Notice it is strictly increasing, and so it will be 1 to 1. It does pass the horizontal line test. And here we have the graph of our inverse function. That's right here, that we obtain by flipping this graph about the main diagonal. And as I just said, the function f, since it is strictly increasing, it is 1 to 1, and so it will pass the horizontal line test. So every horizontal line only crosses the graph at one location, and because of that, the inverse function here will pass the vertical line test, and so the inverse is in itself a function. Now we don't have an equation for the inverse function here, but I do know that it does exist and it is a function. It would just be a little difficult to try to solve this equation. It would be a little difficult to try to solve this equation for x strictly in terms of y, but we know it could be done. And here would be the graph of your inverse function. And that concludes our discussion of inverse functions.